The project I'm going to talk about today is called RoboArm Satellite Positioning Simulator Part 2. Our team members are Shen Hengshuo, Deng Qiaosong, and Boxiao. And our sponsor is Dr. Lipsett and Dr. Knudsen. Thanks for sponsor again. So this is a poster for our project. It consists of 6 parts. The first part is the introduction part. It briefly describes the reason why we do the project and the usage for our robot arm. The second part is the use cases part. It explains the specific steps or actions taken by user or system to achieve their goals. In the works part, it's easy to understand this. It just shows us what robot arms literally does and how researchers use the software to control the robot arm. In outcome part, this part demonstrates the expected outcome for our project, like support the 3 kg weight and full extension, and what did work and what didn't work for our project. And the last part is a future consideration. This part shows what we need to fix or update in our project, including both hardware and software components. And so this is the introduction for our project. The AlbertaSat and U of A academics lay tools to simulate and model satellite motions, which makes testing attitude control challenging. A second robot arm on the RASPS rail system is needed to model and simulate satellite motions and address inter-satellite communications and capture of the decrease of satellites. These projects aim to design and implement such an arm connected to RASPS system from the Part 1 to facilitate satellite development research and testing. This is a use case for our project. You can see the operators can set the instruction on the software to the robot arm. You can see it's in the left side of these pictures. And by using the mouse and keyboard, and then the software translates and sends the instruction to the control board of the robot arm. The control board will receive the commands first, and then translate them into G code and send it to the motor drivers. And the next step is the motor drivers will rotate each joint according to the G code. By the way, if there any emergency happens, we set an external emergency button for pressing, and it will stop robot arms or actions immediately for the safety, And then this is a system architecture for our project. The robot arm system consists of 2 main subsystems. The robot arm itself and the software running on the Windows operating system. You can see which one is. There's a 2 part in these pictures. And the major nodes and components of each subsystem are identified below. You can see the power supply supplied power to the control board, which is in the middle, and the emergency button. The computer operates the control board, which consists of emergency brake button. You can see in the left bottom this box. Both of the motor drivers and encoders drive the step motors. At last, robot arm joints are driven by the step motors to finish the task. And the next part is well introduced by my teammates Deng Qiaosong.
Okay, I'm Qiaosong Deng. I will introduce you what role this robotic arm plays in research and the way it works. I will also tell you what our expectation for this arm, in other words, its requirement, and what our final prototype looks like. As we said before, this robot arm can help researchers to develop Earth satellites. To achieve this goal, the front end of the arm can be replaced with a variety of tools. So you can replace it with a satellite model. Then you can design the trajectory of the front end of the arm on the software we provide. In our design, this software can also control the robotic arm designed by Group 1 so that you can design the interactive motion of multiple satellites through the same software without switching the software back and forth. Now I will show you what our ideal software interface looks like. In all software, you don't need to think about the angle and speed of each motor rotation, such as very detailed control problems. All robotic arm is divided into three parts: the tool frame, the robotic flange, which is the port you use to install the tools, and finally, the base frame. All you need to do is to determine the relative position of each part, and all software automatically controls the motor through a series of calculations to move the arm to the desired location. We also provide for you to set up your own frame of reference. You can set the frame of reference on the base of the arm. You can also set it anywhere you want, and then you can control the front end of the arm to move relative to this new reference frame that you set up. For advanced player, we also give them more detailed features, such as setting the rotation speed of each joint or the rotation angle. Please look forward to our follow-up updates, although the wait time may be forever. We also have some basic requirements for our robotic arm, such as supporting a minimum weight of 3 kilograms at full extension, and supporting a minimum motion of 5 dimensions. Because of time constraints, I'm not going to go over every requirement here. If you want to know, please read our design report for more detailed explanation. Now we have to come to the demonstration stage of our prototype. Unfortunately, due to the lack of certain types of screws and bearings, our robotic arm has not been fully assembled, and even the beam at the top has not been installed. We have tried our best to show it as when we envision it, but due to some force major factors, for example, the two largest motors at the bottom are all broken, and we cannot order the parts we lack in a short time. So the assembly plan had to be put on hold. But please don't give up hope on us. We will show you our excellent professional quality in the following 5 minutes, although it's in the alternative project. Now I will hand over the presentation to our last member. Welcome to Shen Hengshuo.
Due to the original project not working out as expected, we made the decision to shift our focus to a mini project involving the creation of an automatic etch-a-sketch drawing board. This allowed us to gain hands-on experience with motor control. The drawing board features two knobs at the bottom that are controlled by two motors. A control board which can execute G-code is used to control the motors. In the next segment of this presentation, I will demonstrate how to use this drawing board. To begin, I will need to establish a connection to the local server. However, with some modifications, it is also possible to run this application on another device and send requests to the computer that is connected to the control board. Once the connection is established, I will select the correct serial port. This will take us to the home page, where we can select an image to be drawn on the etch-a-sketch drawing board. After choosing an image, a preview of the expected outcome is displayed. The image processing and the generation of corresponding G-code file is done at the server side. If you are satisfied with the preview, you can click the Start button to let the board begin drawing. final outcome looks great. Let's try another image. Click the Start button again. In addition to these features, there are other functionalities that we can explore. For instance, if you have a prepared G-code file, you can send it directly to the control board. You can also choose from a variety of default shapes to draw on the board. Finally, you can send G-code commands one by one from the client to the control board. That's all for this mini project. I hope you enjoyed this demonstration. Moving forward, let's discuss potential ways to improve the original project in the future. Let us talk about hardware components first. Firstly, we can focus on assembling the robot arm once all the necessary materials have been delivered. In addition, we should aim to install better motors in the robot arm to ensure it can support a load of 3 kg at full extension. End stops. They are used to ensure the safety of the robot arm and prevent any potential damage. We plan to add end stops to the robot arm. These end stops will serve as a physical limit to the movement of the robot arm and will programmed to prevent it from moving beyond its safe range. The last component in hardware is emergency brake button. It can be used to ensure the safety of users and prevent any potential damage. We will add a kill switch to the robot arm. This switch will be designed to immediately shut down the robot arm in case of any emergency or malfunction. Let's move to the next part, software components. So first one is GUI. We will develop a user-friendly GUI to allow users to control each joint of the robot arm individually or set the gripper to a certain position in XYZ coordinate. The GUI will provide an intuitive and easy-to-use interface for users to interact with the robot arm. Next is API. As the robot arm will be controlled by software that also controls another robot arm, we plan to develop an API to enable the software to control the robot arm. The API will provide a standardized interface for communicating with the robot arm and will enable integration with other software tools. Motion modeling software. To meet the AlbertaSat requirement of being able to model and simulate the motion of one or two satellites relative to each other, we will develop software that can coordinate the motion of two robot arms. This will enable research and development related to the inter-satellite communication, capture of dead satellites, and other related problems. The last topic is reverse kinematics. We plan to develop the reserve kinematics of the robot arm. The reserve kinematics algorithm will allow us to determine the joint angles required to achieve a desired end effector position and orientation. This will be essential in allowing the robot arm to perform specific tasks and operate autonomously. By developing reverse kinematics, we will enhance the capability of the robot arm and enable it to perform a wide range of complex tasks. Finally, its conclusion. During our project, we faced some major obstacles concerning the delivery and availability of materials, as well as damage to a few of our motors. However, we adapted to these challenges and altered our project's focus to control and etch a sketch using motors, allowing us to draw user-defined artwork. Our team was able to successfully complete this portion of the project, which provided us with valuable experience in developing both software and firmware related to robotic arms. We are confident that our work will serve as a good starting point for future teams undertaking similar projects. Thank you for listening.